Welcome to the PetroPapers podcast. Say that 10 times fast. This is where you get your oil and gas intellectual stimulation by asking the technical questions. I'm Yogesh Pradhan, and with me here today, I have Malcolm Kintzing and Faye Liu from Revochem and from Henry Resources. I'm going to talk about SPE 209145. Paper title and the description is in the description box below for our viewers and listeners on Apple Podcasts and YouTube. Now, I'm going to give an introduction about Malcolm and Faye. Just give me one moment. Malcolm Kintzing is currently an engineer and business development coordinator at Henry Resources. He specializes in completion design and reservoir development optimization. Strong believer in continuous improvement through technology and technical collaboration. Malcolm has co-authored SP papers on evaluating limited entry perforating with perf imaging and fiber optic DTS warmbacks and frac drainage height with geochemical fingerprinting. Before joining Henry Resources in 2020, Malcolm was a completion design supervisor and senior reservoir engineer for SM Energy. He's graduated from Montana Tech in 2010 with a Bachelor of Science in Petroleum Engineering. Now, I'll talk about Faye Liu. Dr. Faye Liu is the founder and CEO of Revochem, technology company with patented lab procedure and data analytics and tools in high resolution, high fidelity geochemical fingerprint data from the oil. She's worked at ConocoPhillips as a senior geochemist for 6 years and pioneered the application of geochemical data as a reservoir monitoring tool. She then founded Revochem with her husband, Dr. Jiang Wu, who's a biochemist with many years of experience working in the medical field. Together, they adopted and optimized several chemical analytical methods from other disciplines, including medical, food, and environmental areas for modernized geochemical analysis and data analytics using geochemical data. Faye has experiences using geochemical fingerprint technology over thousands of wells across various basins. She holds a PhD and MS in geochemistry, both from Indiana University, Bloomington. She also holds a BS in environmental engineering. She has first co-authored over a dozen peer-reviewed papers, which have been cited over 600 times globally. She also serves on the advisory board for IU Earth and Atmospheric Sciences Department and a recipient of the IU 20 Under 40 of 2020. So Faye, welcome back to the podcast, and Malcolm, welcome to the podcast.
Thanks, Yoshi.
Thank you.
Well, before I start peppering you all with some questions specific to the paper, I was wondering if either of you can start off with just walking through the paper to orient our viewers and listeners.
Malcolm, do you want to go ahead?
Sure. This is a project that we got started a couple years ago. I've seen some of Revochem's previous work and was always interested in it. We ended up drilling a pad, in the Midland Basin, targeting 3 intervals. And, initially, the wells, came on good. But we definitely were seeing some pressure communication between the wells. So we knew there was some communication. We were wondering if, we either had, if we needed to drill, 3 targets, or if we could, just drill our future wells, just targeting 2 wells. And that's what really kind of spurred my interest in doing some geochem here. So with that, we started, by just grabbing a couple of oil samples and looking at some of the geochem that Faye does. And then at the same time, we were drilling a pilot hole in the area, which gave us the perfect opportunity to grab some rock samples to get a baseline for this geochem. So once we were able to get the baseline for the geochem, we already had the initial pad that targeted 3 intervals. We also were initiating another project adjacent to this, where we're only going to target 2 intervals. So we already had a setup for testing 3 intervals for this development area and 2 intervals. And we started producing those wells and continued to collect samples. And we did the geochem work. It showed a lot more overlap in the development, where we were targeting 3 intervals versus the 2 intervals. But then we started to dig into the production. I'm an engineer, reservoir engineer, so that's part of my job, is to run economics and figure out the most optimum development. And when we started comparing the production to the geochem, we were getting some really good relationships, and that's what kind of spurred the idea of writing a paper on not just the geochemical fingerprinting, but adding on the production, or how the geochemical fingerprinting is relating to the production we're seeing with these different developments, and how it may impact how completion design may be impacting the results we're seeing here as well.
Awesome. I know that when I read the paper internally, it was definitely something of interest for our group. So it was kudos on the paper. I really enjoyed it quite a bit.
Yeah, thank you for that quick summary, really good summary for all the background and application. I also wanted to add a point from more on the technical side, from the geochemistry technology aspect, that it is also our first publication on understanding the lateral well fracking and lateral well communication, because previously all the geochemistry study, production location, drainage, frac height, it's primarily relying on the vertical distinction, which is what we traditionally know about those geochemical information, that they varies vertically because geology changing much faster vertically. However, it's also changed laterally, but much more subtly and much slower than it's changing vertically. So having the ability to also understand how the frac geometry is both vertically and laterally have been a challenge, particularly on the lateral part. So this paper is our first time to have a semi-quantitative tool to understand also laterally, because that's not just stacking, but also how you space your wells. So that for us, that's a very unique aspect on the paper, and also be able to correlate how the frac geometry is to the production to explain the performance of the well. That's also a very interesting aspect, and very, very unique aspect of that paper.
Awesome. So this question's for you, Faye. I noticed you talked a little bit about the technical side, and I was wondering if you can get into a little bit into the details of that. Could you describe how to determine the SI lateral and SI vertical, that similarity index?
Yes, absolutely. Yeah. So in your previous episode where we talked about production location, when we reviewed that 2020 ERTAC paper, that sort of give the overview of how you tie the oil back to the rock, to the baseline, which is more of a traditional way of doing production location. You use each of the rock sample to represent the vertical interval, collect this geochemistry information, and compare it to the oil to do so. As we do more and more of production allocation, we realize the vicinity, having to be in the vicinity of the baseline is a key limitation for the technology, because we started to notice as our knowledge grow in the basin that when you move further away from the baseline, then the geochemistry information for the same interval, let's say for the same upper Wolfcamp A for the first 20, 30 feet, if you measure same equivalent depths in point A versus 5 miles away, you would get a bit different signature. Sometimes it's negligible that compared to the vertical difference that you can ignore it and assume just geology don't change laterally. But as our control point grow more and more and we get more and more data, we realize in a lot of places that is not a valid assumption anymore when you are 3-5 miles, sometimes further away from the baseline. So that become a limitation, and we started to think, is there any other way we can be able to still utilize the information without the baseline? Because the information that are in the oil is still there, regardless you have a baseline or not. It's just when you have a baseline, you'll be able to have a reference point to translate it better. So then we go back to what's in the oil. So when you think about it, the oil represents the drainage rock volume of that well. So the oil represent our we call it drainage rock volume, DRV. So in other words, the more similar the drainage rock volume are between the two wells, the oil should look more similar. So based on that, that's how we develop the similarity index. So we look at how similar those two oils are, whether they're, 30% difference, 20% difference, and then using that to represent how two wells are, how much they have overlapped drainage. And based on empirical data, we established, because we have a lot of baseline, we have over 2,000 wells we're actively monitoring across different basins, particularly, I would say 50-60% of that are in the Permian. So we have a lot of data over a broad area. So which allow us to study what are the sensitive geochemical information that are sensitive to the vertical difference, and also what are the geochemical information that are more sensitive to the lateral change. So particularly when you have a pilot nearby, you have a cutting or core baseline nearby, you can study that core or cutting, which is the case that in Malcolm's case, we can study that pilot cuttings to know, okay, those ratios, we know it follows a very good depth trend. So it's more sensitive to the vertical change. That are the group of compound we use to calculate the similarity index vertical. And by studying the producing well over a wider lateral range, we also have knowledge of what are the compound that tend to change more with the lateral change. I'll be honest that the vertical is still the primary change. However, the Midland Basin, in a lot of places, the lateral change are also pretty fast. So when you're getting we know that by having wells that are from the next pad, there's lateral variation. So there are also a group of ratios we sort of find out empirically that are sensitive to the lateral change. So that is the group of ratio we use for similarity index lateral SIL calculation. So essentially, the production allocation allocates the oil against the vertical baseline, while similarity index, in lieu of the vertical baseline, looking at relationship between two wells.
Okay. Awesome. Thanks for that clarification.
Yeah, absolutely. Yeah, it's production allocation is more straightforward. It's more of a clean calculation quantitatively. So it's very easy to understand. We don't need to explain a lot, the results, you see how it's draining from. The similarity index, I admit that's, I do have to say that it's the calculation itself is simple and it's very straightforward, just to look at how similar two oils are. However, it is a more sensitive data just because it looking at even wider chemistry, geochemical ranges, and it can be more sensitive to anything happening to it. Vertical, they're just changing in this direction. When you have the lateral change to it, when you have two geometry, how they maybe vertically different also changes how it overlap laterally. So it's a much more calculation is simple, but into how to properly interpret the results needs more time or more integration with other data.
Of course.
Mhm.
Malcolm, I was wondering if you can comment on the completions design for both the pads that were mentioned in the paper, as in, do they have the same proppant loading and cluster spacing?
Yep, sure. Yeah, so both of the pads, we had a 4-well pad targeting 2 intervals and then a 5-well pad targeting 3. Both developments utilize the same proppant loading, same fluid loading. But the 5-well pad did use a different perforation design. It was a 2019 completion. So it had approximately, 20-foot clusters, a few more perforations per stage. And then the 4-well pad did utilize, tighter cluster spacing and a more limited entry perforating design. So, you're never going to have a perfect test where everything's equal. But, same fluid and proppant, but, probably a little bit better frac on the 4-well development.
Sounds good. When SIL and SIV change over time, so the similarity index, the lateral and the vertical, what do you think are some implications of the drainage area? Do you think we're seeing fracture closure?
Do you want me to take that, Faye? Okay. Yeah. So, that was really interesting. First talking about the vertical drainage. A lot of times we think that we're going to be draining a big area initially, and then it's going to start shrinking. But when we were just looking at the vertical drainage index, we actually saw that initially we were draining a lot closer to the well bore, and then as we continued to deplete these wells, the vertical drainage actually increased over time.
Wow.
And that's one thing, and that was some really valuable data from this geochem, because we did some pressure testing early on, and we saw lots of vertical communication, but the thought was, well, maybe that'll just go away over time. But it really hasn't. And the geochem really confirmed that as well, is that this vertical drainage was increased over time, and it was there to stay. Then the lateral index, it was pretty interesting. It was actually the inverse of that, where initially it looked like it was a little bit further out, and then as we produced the wells, it came in. So that was it's really interesting that, I guess our vertical drainage was increasing, but then our lateral drainage was decreasing over time. So it really showed us a lot of the dynamics we may be seeing between these wells, and the implications for it are future development configurations. Maybe we don't want to stack our wells at all, and we could possibly stagger them in a little bit tighter configuration, but avoid stacking altogether.
Awesome. And I guess you answered a little bit of that next question I was going to ask, in terms of implications of that pressure pulse test that you've seen, and then the similarity lateral and similarity vertical index seen on the geochem side. So what are some implications on that pressure pulse test? It looks like the vertical drainage is here, like the vertical drainage is pretty prevalent, and then the lateral drainage, there's actually more closure coming from your lateral.
Yeah, that's exactly what I think we saw there is a lot more vertical drainage that doesn't seem to have a lot of closure, or doesn't seem to go away, but then a lot less lateral drainage. So, both the pressure data and the geochem showed the same thing, less lateral communication, more vertical communication, which, can help us, improve our future spacing configurations.
Awesome. I was curious to know, and either one of y'all can answer this question, but how do we know there aren't any other parameters at play that contribute to that marginal production variances on pad Y, but there were large production variances on pad X? So one of them was the 4-well pad and one of them was the 5-well pad. I believe the 5-well pad was X and the 4-well pad was Y. I don't remember, but there were marginal production variances on pad Y.
Yep. Yeah. So yeah, relatively similar performance in all of the wells in pad Y. Yeah, that was the 4-well pad. And then, the 5-well pad, we saw a wide range of production differences. And, I really think, just the wide range of production differences in that 5-well development is just part of the communication. We're seeing a lot of communication between those wells, and one well is probably stealing production from the other. And even another trend we saw that we didn't mention in the paper is the first wells we brought on that pad are the best wells, and then the last one we brought on is the poorest. So even there's not a huge time difference. There could have been so much communication between those wells that just the matter of the order we turned them on may be playing a part in that variance in performance as well, just because of how much communication we saw. And then for the consistent performance in the 4-well pad is there was less communication observed. So maybe you're seeing just kind of all of the wells, there's some communication between them, but you're able to see more consistent results because there isn't as much production sharing between the wells.
Interesting. No, it's interesting that you mentioned that, and the fact that when the first couple wells were turned on, yeah, they were definitely stealing production from those other wells. Wow. That's an interesting insight. Faye, I was curious to know, how can viewers and listeners interpret geochemical variation results that were shown in the paper?
Are you saying the geochemical variations through time that you
Yes.
see? Yeah. Okay. Yeah. So so those are what we observe. So we collect the oil samples. It's Malcolm's team collect those samples, send over, and we measure them. And the variation we see in those oils, and well, it's actually when we go back to in a very early time when I initiated time-lapse program in my early of my career, because typically geochemists' job are finding the oil. We're typically involved with the exploration project, so studying the salt rock and looking at the oil generation potential and all that. So there's geochemistry is not a routine, like there not many people routinely monitor produced oils through time. So at that time we had some budget and be able to see that and notice there's actually very noticeable variations through time. And that's what actually triggered the entire time-lapse geochemistry program. That, okay, those variation, at first we thought it was noise. We run a lot of repeat samples and it's not noise, it's the difference or solid difference, much larger than the analytical error bar. So there's some solid changes in the oil signatures that could be correlated with the vertical drainage difference, because the geochemistry difference, if you look at the subsurface, whether it's core or cutting, the key thing that are driving those geochemical difference are the vertical distinction, because they have different depositional environment and they have different mineralogy and also different migration pathway. For example, if you hydrocarbon migrated, let's say from Wolfcamp to the Dean, it's passing through kerogen, passing through clay and different mineralogy. Certain compounds have high affinity left behind, certain compound accumulating more in a salt rock zone versus in the reservoir zone versus some left behind in a salt rock zone. So we found those geochemical variations are really indicating how the well are draining from different part of the reservoir. And the first order control is the vertical. That's how the rock deposit and they migrate. So that's the first order control. So using geochemistry information to understand zonal contribution. So that's the first application. And that application in the conventional reservoir actually started from the 80s and 90s. So it's not in a conventional reservoir, that's not a new technology. It's being recognized in many countries, and Norwegian government do recognize it as a valid way to calculate royalty. So it's being validated against production logs and others. So we know that technology works to identify those vertical distinctions. When you move on to the unconventional reservoir, there's a different level of challenges, just because, conventional reservoir, we're dealing with telling the difference between maybe 3 or 5, less than 10 different zones that we need to distinguish. For unconventional, it's a continuous zone that is, we wanted to tell the difference, every 10, 15 feet, so that we can understand is my frac is 200 feet, 220 or 250. So that gives much higher requirement for the resolution needed to tell about those fine granularity difference. We know your Middle Spraberry versus Wolfcamp, there's a difference, but within the Wolfcamp or within the Mid Spraberry, every 10, 15, 20 feet, we wanted to see which part of the reservoir have been more fully utilized and what have been less drained, or the drainage have, maybe there in the beginning, but diminished very quickly in a few weeks or a few months, so that okay, when I calculate my recovery factor, I know, the time element is also a very important one, because, how fast those will decline, all that. So really, the time-lapse variation have been first interpreted versus its vertical baseline to translate into how the drainage varies vertically. And then understanding its lateral is more of our newest understanding, like with more and more data, which allow us to screening through the data and understand the lateral change. Ideally, we would want lateral cuttings. That's essentially, we did that vertically. That's perfect. If we have lateral cuttings to understand the lateral change, ideally you could just do that laterally. However, it has its own challenge, right? I mean, first, the geology don't change as fast laterally, but we do have access to some lateral cuttings, and they're not that every 10 or 15, 20 feet, but every couple of 100 feet, you do see some variations. But unfortunately, most of the lateral wells are drilled with oil-based mud cuttings, which we, have contamination issues, so we cannot use that. So the alternative way that we come up with, it's not completely quantitative. It's not like we can tell each stage or section how much are coming. But between the two different wells, we still be able to see if there's more. And when you have a controlled experiment, other things equal, right? We could still see, okay, why? Let's say it's all Wolfcamp A well, so that lateral variation, that background change should be at similar speed. If you have two Wolfcamp pairs that are with the similarity index lateral much more similar than the other pair, then that meaning those two wells are definitely have more laterally overlapped drainage. Exactly how much overlap, are we overlapping, I don't know, 300 feet or 200 feet? We're not there yet. We can only say in a comparative way, those are definitely much stronger. And also across those thousands of wells, we sort of build a knowledge saying, okay, between Wolfcamp A well in the Midland Basin, in the Northern Midland Basin or Southern Midland Basin, that number, we typically observe a 3 to 5 or whatever number is. So when you see a number abnormally high, then, from a statistical perspective, it is on the higher spectrum of what we see. And if at that time we can further correlate that with performance, and then we can come up with a more of an empirical understanding. Okay, I don't want my spacing. I've seen that done in we have some clients are doing that in the Eagle Ford, that they're able to collect a variety of different spacings and collect the SI number. Then they can correlate with performance data and see, okay, once my spacing is tighter, let's say 500 feet or 400 feet, I'm just making that up, then they started to see a compromised performance in their well. So they know, okay, in this bench, in this basin, in this area, I will be very careful if I wanted to space my well tighter than 500 feet, because I see immediately SIL increase and I see a compromised production. So yeah, and when you are, and you can carry that learning into a wider area, in the area that you newly drilled, but in the same bench, you say, okay, I can monitor my SI when I don't have enough data yet. But if it's, significantly higher than where I typically wanted to avoid, that at least it's an early warning sign, whether you could potentially run into an overstacking or spacing problem.
Awesome. Thank you for that information. That was extremely insightful.
Absolutely.
Malcolm, I know you talked a little bit about this in terms of what decisions can be made, but I was thinking to wrap it up, and you mentioned this in your presentation at HFTC with respect to well spacing, but what decisions can you make with the technical work that was shown in the paper?
Sure. It really all boils down to, economics, and pad or development economics going forward. And so, I think in my presentation, I said, the political answer, really depends on your company's, rate of return thresholds and economic metrics. But, I think the bottom line is, with the 5 well, three bench development, we saw a lot of communication between the wells, and it did hurt the EUR and resulted in more capital costs. The 4 well development is going to sacrifice some inventory, but you're going to spend less capital and end up with slightly better wells. So if you're just looking at capital efficiency, the lower well count, better well performance is always going to win. So the real question is, that incremental capital you have to spend to get that incremental production from the increased development. What kind of rate of return are you getting on the incremental capital? And that's always depends on your inputs. What is the D&C costs? About a year ago, D&C costs are pretty low, and right now they're coming up quickly. But that's a function of oil price as well. Oil price is looking pretty good right now at about $110 a barrel.
Yeah.
So it really depends on the environment and what your outlook is on oil price and D&C costs. So it's hard to say what's the correct answer, just because there's so many inputs into it. But for me, the safest answer with so many variables out there, and how our industry can change, so quickly. The more, conservative choice, capital efficiency, is the way I tend to lean.
Awesome. And yes, it does depend, it does boil down to the economics and does depend on a company's rate of return thresholds to make their decisions. Well, thank you so much, both of you, for being on this podcast and letting me pepper you with questions.
Absolutely.
Yeah, absolutely. It's a pleasure.
Well, you heard it straight from Malcolm and Faye regarding SPE 209145 and letting me pepper them with questions and all their great insights. Please let me know what feedback you have regarding the podcast. I'll have my email in the description box, as well as the paper citation if you want to take a read of more details of SB 209145. I'm Yoga Shri Pradhan, and I'm signing off.